So, good morning. Hello, everybody. So, I'd like to start my talk by thanking How Dong for this kind invitation. Actually, it's my first time in China, and I'm really enjoying to be here, and I'm glad to contribute in this meeting. So, today, my talk, in the first part of my talk, I will be presenting you a very general argument about the three-state model. I have only 3 slides to go, so very brief. And in the second part, we're going to be applying this three-state thermodynamic model to study the interaction of general anesthetics and ion channels. So, as you know, membrane proteins can respond to a variety of stimuli in nature in such a way that we can describe their state probability as a function of the number of intensive variables in our system, like temperature, the surface tension of the membrane, the transmembrane voltage, or the chemical potential of protons. And if membrane proteins are further regulated by small ligands, so ligands may induce this kind of shift in the state probability. So in a very broad way, we may rationalize this kind of probability shift in terms of this simple thermodynamic model, where the ligands, shown here in yellow, may bind the two-state membrane proteins at a given conformation. So we're talking about a protein with 2 well-defined states, let's say closed or open. And if the ligand binds the protein in a preferred way, so it may shift the conformation equilibrium of the protein. So what I want to do in the first part of my talk is to solve this thermodynamic cycle. And to solve this cycle, we start by looking at the protein, as shown here, and its immediate vicinity, including the membrane and the water, as an open molecular system. So the system is in contact with a bath with a well-defined temperature T. The ligands have a well-defined density, and the bath has a specific property chi, any given intensive property that can be controlled externally. Because the system is open, so ligands may migrate from bulk into the system and reversibly. So under this configuration, we may define this effective potential energy of the system in terms of the internal degrees of freedom of the protein and the membrane, plus any given centroid distribution of the ligands, and plus chi prime, which is the energy resulting from the coupling of the system and the bath. So chi prime can be expressed as a number of intensive extensive conjugates, and typical conjugates appearing in biology are the following. So the effective charge in the system, Q, and a given applied transmembrane voltage, V. So a given lateral area of the system and the surface tension of the membrane, or a given number of bound hydrogens and the potential chemical of this species. So by defining this effective energy, we may define the free energy change between conformations of the protein, let's say X and Y, for the specific situation where all ligands are in the bath. So this is the conformational free energy change for the protein free of ligands. And from here we may get derive the familiar two-state Boltzmann equation, which gives you the probability of the protein to be in a given conformation X when the bath has a specific property chi, in terms of these 2 free energy quantities. So this is the free energy for the change of the conformation of the protein at a given reference value, plus this excess free energy, which informs you the coupling of each conformation with the external bath. So this model is very popular because actually we can fit the experimental data into this equation, and you can learn these two quantities in terms of experimental parameters. So that's so popular among experimentalists. So to keep solving this thermodynamical cycle, we wanted then to solve the binding problem. So we're talking about small ligands, so we're talking about low affinity binding. So probably we want to solve this generalized reaction process here, where the protein can be interacting with more than one ligand under complex saturation and concentration effect. So we are talking about multiple sites, and one or more ligands can bind the very same site at once. So to solve this generalized reaction, we want to solve the bind constant for this process from the definitions of solvation-free energies. And this solvation-free energy reports on the reversible work to transfer the ligands from gas phase into the molecular systems. And knowing this, we may define this generalized bind constant in terms of this ratio between two configuration integrals. So for the situation where all ligands are in the bath versus the situation where the ligands are in the bind sites. And of course, this bind constant must handle the fact that ligands are indistinguishable and that they have a specific density in the bath. So once you know this bind constant, actually you can reconstruct the thermodynamics of the system. So we can define the probability of the channel or the protein to be occupied by any given number of ligands. And you can also describe the three-dimensional distribution of ligands in the system. So these two quantities here are concentration dependent, which is formally shown here. So they can be very important for biochemical studies. And finally, and I'm almost done, if you link these two processes, you may derive the very same Boltzmann equation, but now taking in consideration the relation between these two Graham-canonical partition functions. So these partition functions take in consideration the bind affinities over all occupancy states of the channel at a given conformation. And the meaning of this equation is very straightforward. So if the ratio is 1, it means that ligands may bind the two conformations of protein with the very same stability. If it's larger than 1, it means that it binds the Y state and shifts the probability in the right direction, otherwise in the left one. So this equation is very general, and it can be applied to a variety of biochemical studies. And where we are applying this, we think this can be important to study the interaction of the general anesthetics and ion channels. So general anesthetics encompass a great variety of small uncharted ligands like propofol, halothane, and sevoflurane. And despite efforts reaching back over a century, their microscopic action in general anesthesia remains largely unknown. A favoring hypothesis supports that ion channels in the brain are implicated, and key players have been identified, like the inotropic neurotransmitter receptors, voltage-gated ion channels, and non-gated ion channels. And the consensual view here is the following. So general anesthetics somehow may change the conformation equilibrium of ion channels. And by change that conformation equilibrium, they may affect their overall conductance and therefore the overall excitability of neurons to induce anesthesia. So a first mechanism, the so-called membrane-mediated mechanism, was proposed for this anesthetic action, and it states the following. So general anesthetics binds to the membrane, and because ion channels are membrane-embedded proteins, they may somehow, in a very non-specific way, impact ion channel energetics. But that mechanism has shifted towards a more specific bind problem, where now we expect that anesthetics, despite their low affinity, may bind ion channels directly to impact their function and energetics. So, among other reasons, this shift occurred because, well, we know these days that at clinical concentrations, general anesthetics may well affect lipid bilayer properties. And more importantly, a bunch of recent high-resolution measurements, include X-ray, crystallography, and MD simulations, show that anesthetics bind ion channels directly. So what is the fundamental structural hypothesis here? Is the following. So anesthetics bind ion channels, and more importantly, bind in a conformation-dependent way to impact energetics. So this is exactly the kind of hypothesis we want to investigate here in the context of this voltage-gated potassium channel Kv1.2 and the sevoflurane, which is a general anesthetic. So Kv1.2 is largely expressed in our brain, and sevo is widely and commonly used in hospitals. And in recent years, Kovalubias and co-workers, including myself, showed very clear that at 1 millimolar concentration, sevo potentiates Kv1.2. So there is this leftward shift in the conductance of the channel, and its maximum, and this increase in maximum conductance. So this is an experimental curve. So what do we want to do? We wanted to reconstruct this shift in the open conductance of the channel, in the open probability, in terms of this two-state thermodynamic model, where the anesthetic binds the resting close and activated open state of the channel. And why we are particularly interested in this cycle? Because over the years we have accumulated structural information for these states of the channel. So in a very brief way, starting from the open X-ray structure of the channel embedded in a phospholipid bilayer and simulated under an applied voltage, we could follow and sample the down state of the channel. So in these simulations, every time you have protein charge moving across the transmembrane field, we have to rebalance the electrolytes to keep the applied voltage constant in simulation time, as shown here. So fluctuations of the applied voltage store information on the instantaneous gating charge going across the transmembrane field. And here is a typical gating charge versus time profile we can record in this kind of simulations. And what is happening here is that the S4 segment, which is shown here, which is a positively charged transmembrane field, is moving across the transmembrane field. And it's pushing this S4-S5 linker, which is this green part of the protein here, to close the main pore. So this final structure here, which is the resting closed structure, it complements most of the experimental data, and more importantly, it accounts for the transport of 13.2 electric charges across the field, which is pretty much consistent with experimental estimates. So there is now in the literature a consensual opinion that these two structures, atomistic structures, are representative of the up and down state of the channel. So what do we want to do? We want to export these structures to solve this thermodynamic cycle. So we start by investigating the interaction of sevo with the open structure of the channel. So we relied on docking calculations and free energy perturbations to solve and to find bind sites and to solve bind constants for each of these sites. So first we generate a large ensemble of structures, and then we dock. I mean, we get like thousands of docking solutions that could be clustered in 3 bind sites. On top of the S4-S5 linker, which is this very important piece of the machinery, shown here in orange, at the S5-S6 interface, shown here in blue, and outside the channel, next to the selectivity filter, shown here in green. And because we were also interested in saturation effects, we investigate also the bind of 2 molecules in each of these bind sites. So we redock sevo in each of these bind sites. So we could find double occupancies for sites at the S4-S5 linker and S5-S6 interface, but not at the filter. So, and here are molecular views for single and double occupied sites. And from the docking, we could apply free energy perturbation calculations to get the free energies for transferring the ligands from gas phase into the bind sites, and more importantly, to get the single and double bind constants in each of these bind sites. So here, bind constants are shown in millimolar units, and I have to say that we have performed at least 2 replicas of free energy calculations to get these numbers. So I would like just to emphasize that docking was performed in vacuum, but FET was performed under explicit environment. So lipid, water, ions, everything was taken in consideration when solving the solvation free energies. And because bind sites are sparse on the molecular surface, we could solve the generalized bind constant under the assumption of independent bind sites. In this case, we may factorize the bind constant in terms of per site contributions. And once you get these bind constant, as I mentioned, you can reconstruct thermodynamics. And here I show you the probability of the channel to be occupied by any ligands, regardless their site distributions, as you increase concentration in the bulk. And you see that as you increase, you start populating more and more the channel. But you populate the channel in a site-specific manner. So there is a high affinity for the S4S5 linker, for the S5S6 interface, and really a very, very low affinity at the selectivity future. So we may visualize this distribution in terms of three-dimensional maps. And here in blue, I show you the density of the ligand on the surface of the channel as you increase concentration. And the major conclusion here is that at 1 millimolar concentration, which is clinical, you get already a resolved density of the ligands on the S4S5 linker. And as you increase concentration, you populate more the channel. So the conclusion is that SIVO binds the open structure of K1.2 at the S4S5 linker and the S5S6 interface, which is highly consistent with experimental findings. So we knew that mutations in the S4S5 linker drastically impact the interaction of anesthetics in the ion channels. And more importantly, and more recently, Eckenhoff and co-workers showed from photolabeling experiments that SIVO may protect the S4S5 linker and the S5S6 interface from binding of SIVO-fluorine analogs. So, which is pretty much consistent with our calculations. So our first problem, our next problem, was to solve the interaction of the ligand and the whole transmembrane domain of the protein. So we extended our docking calculations now to explore interaction sites on the voltage sensor and in both conformations, the open and closed one. So here's the space of docking solutions for each of these states, and we could recapitulate the very same sites on the pore, S4S5 linker, S5S6 interface, and new sites within the voltage sensor and at the interface between voltage sensor and the pore were determined. And following a very long series of FET calculations, we could solve bind constants for the 2 conformations of the protein, X and Y. And we could investigate in more detail the conformation dependence between these structures. And here I show you the 3-dimensional distributions for the closed and open structures, and they are different. And there is a clear conformation dependence as the number of average bound molecules in the open state increases towards the open state. So what is the impact on the energetics of the channel? So by rewriting the 2-state Boltzmann equation in terms of these thermodynamic conjugates for the channel, which is gain charge and applied voltage, we could reconstruct the experimental curves. So here I recapitulated the experimental profile in black for the free channel, the experimental profile at 1 millimolar concentration of the ligand, and here our reconstructed curves from microscopic binding events. I show you in the range of 1 to 100 millimolar concentration that we can reconstruct the experimental data or this leftward shift in the range of 10 to 100 millimolar. Because bind sites are independent, we may also factorize the partition functions in terms of per site contributions to show that SIVO binds the voltage sensor and the S5S6 interface and stabilize the closed structure, but this effect is largely dominated by the stabilization of the open state when SIVO binds the S4-S5 linker. So what is the conclusion so far? I can summarize here. So we may reconstruct this leftward shift in the open probability of the channel from microscopic events. There is a complex interplay of sites, where sites may bind the closed and open with different affinities, but there is a dominant effect towards the open state. So, but it's true that these conclusions can be very interesting, very revealing, but they may suffer from any kind of dependence on the way you have performed docking and free energy calculations. So we decided to look at a different sampling strategy. So let's look at the problem from a different perspective. Let's perform this kind of flooding MD simulation. So we simulated both structures in the membrane and in presence of 150 millimolar concentration of the ligand. So in these simulations, we see that the ligands bind to the membrane and bind reversibly to the protein. And this is the final equilibrium structure of bound molecules at 5 angstroms cutoff. And here, I show you, despite the fact that the density of ligands in the membrane for both simulations are the very same, there is a clear excess number of bound molecules towards the open state. So 14 molecules bind in excess the open conformation. Among this number, 8 molecules bind the channel in flexible regions. So by flexible I means regions with the root mean square deviation larger than 4. So this bind must be important. So these are regions implicating the gating process. So because given the generality of the theoretical construction here, eventually you may read from the 3-dimensional distributions from the flooding information on the per site occupancies as shown here. And from these per site occupancies we can derive the so-called bind constants for each of the bind sites. And this is important because once you know bind constants, you may derive the distributions in any other given concentration. And from the flooding simulations, we see the very same results. There is a preferential binding of the ligand towards the open state. And what is the impact on the energetics again? So here, I show you the probabilities versus the bind voltage. And now we can reproduce this leftward shift in open probability at the range of 1 millimolar concentration. So these are the very same conclusions that we got from docking and free energy calculations, but from a different perspective in terms of flooding and MD simulations. So, and what about the negative control? So we started wondering about a system that, or a general anesthetic for each peak 1.2 is insensitive. So we looked for propofol. So these are the experimental curves for propofol. Peak 1.2 is insensitive to propofol. And what about these theoretical structural results? So we have formed flooding simulations for propofol at 50 millimolar concentration. So propofol goes to the membrane and binds the channel reversibly. And despite this binding, there is no change in the average number of bound molecules. So propofol may bind the 2 conformations, but there is no conformation dependence. So making sense of this result. So there is no energetics differences in both situations. So what is the major conclusion here? So SIVO binds KV1 at multiple bind sites under complex saturation and concentration effects. The results or the macroscopic curves of SIVO and KV1 might be understood in terms of a conformation-dependent binding and implications of S4 and the S4-S5 linker are visible and can be inferred from studies given their very important role in the gating machinery. So this two-state thermodynamic model can explain this leftward shift from the microscopic curves, but cannot explain the increase in maximum conductance. So according to a kinetic experimental model, we need a third state to be considering this thermodynamic model. We don't know the structure, and this is under investigating at this moment in the lab. So I would like just to finish my talk by acknowledging Manuel Covarrubias and co-workers and members of my group in Brazil. And definitely this work would not be done without the very important work of Dr. Letícia Stock, Dr. Caio Souza, Juliana Rossumi, and Leonardo Cerqueira. I also would like to thank all the agencies in Brazil supporting my work, CAPES, CNPq, FAPDEF, FINATEC, and the University of Brasilia. And again, I would like to thank your attention and this very kind invitation. Thank you.